looks like we are set and rolling. All right, we're gonna pick up with slide number 6. And so there's something that you have to consider when we're, from now on, when we are talking about any kind of numbers except for slope, we have to include units. And that's something that we've mentioned, right? We've kind of made a big deal about the units with density. So units are not going away. I actually just posted in Google Classroom a ton of, a whole bunch of links. Our classroom real quick. And you'll see, okay, so my computer has been really, really glitchy and slow today. Your Chromebook's been that way? Okay.
Good morning. Did you know that velocity measurement?
So, you have to kind of bear with me a little bit. But I just want to show you, I just posted all of our new links, and you're going to see there's a ton of them. All right, so you can see there's motion with acceleration, motion without acceleration. There's units and variables. This is such an important thing because we're going to do speed, velocity, distance, and displacement. And the units are usually what give people more trouble than the numbers. So I'm going to tell you this right from the get-go. The numbers are the units are drastically important. Again, the numbers usually aren't the problem. It's, are you using units at all? Are you including the appropriate units? And if you need a direction, are you including a direction? And so just kind of keep that in mind. We'll keep saying it over and over, but the units and direction are super, super important. So you'll see that kind of reflected with how many different games I have set up. So we have units and variables, motion vocab, and then there's position versus time graphs, velocity versus time graphs, more units and variables, units and directions. So there's all kinds of different practice. So understand that that is a hugely important idea. So vector is one of your vocab words, and this is maybe one of the only, this and maybe scalar, you might not have really heard before. Maybe we've heard vector, but maybe not known what it is. It's not a word we use in everyday language, except in the movie Despicable Me, right? One of the villains, his name was Vector, and we'll watch that little clip at the end here. But for a quantity or an amount, for it to be considered vector, it has to have 3 parts, all right? So it has to have a size or a number, which sometimes we'll call a magnitude, right? But basically, it's the number. It also needs to have a unit, so like a kilometer, a mile, an hour, maybe a degree in Fahrenheit, right? Any kind of unit. And then here is the key. It has to have a direction. All right, so not every quantity or every number is going to need to have a direction, but if it is considered vector, and we'll get into what those are, it has to have a direction as well. So 7 kilometers south, or 5 blocks away, right? It doesn't always have to be north, south, east, west. Sometimes it can just be even more like a comparison, and we'll look at a few of those examples. But typically, if it makes sense that they give you direction in the question, you're going to give the north, south, east, west in your answer, okay? So just kind of keep that in mind. So here's some examples. If we're talking displacement, it might be 2.0 meters, and then in these little brackets, they have the capital N for north. You are welcome to do that. If you would rather do that than write out the word north, either way, I can interpret that. I don't care. I'm lazy, and a lot of times, I will do that. I try to write things out at the beginning a little bit, just so you're like, what's the N again, or what's the W? So you know that those are north, west, east, south, whatever it may be. We also have that combination where maybe it's like southwest or northeast or something like that. So sometimes there can be that combination if it's at an angle. So velocity values are always gonna be vector, and you might have something like 30 kilometers per hour east. So not only do you have the number, not only do you have the units, but you have to include that direction. It's easy to forget. Like, I'm guilty of it too, like, I get it. But anytime you're giving a displacement answer or a velocity answer, you have to include that direction. If the answer is 0, if your number is 0, then I'm not a stickler for you, because sometimes it doesn't make sense to be like 0 kilometers north. Like, so I won't count it wrong on if your number answer is 0. But that's the only time. Anything else, and you have to include that direction if we're talking displacement, velocity, or even acceleration, and we'll add that in too. So vectors are going to be quantities that are shown by an arrow drawn above the letter. So basically we're going to use arrows when we use vectors. The arrows sometimes can show us like the pathway. It shows us the motion. It's a way to describe it kind of using pictures, and just basically we're using the arrows to show the path. That's it. That's what that means. Okay. We looked at vectors a little bit last year when we did our force diagrams. And so, you know, it shouldn't be a totally new idea, but we use those arrows, vector arrows, we call them. Things that are going to be scalar. So we have our two categories, vector versus scalar. Scalar quantities are basically just like vector, except they don't need a direction. Okay, so it's magnitude in a unit or a number in a unit. That's pretty much what we use. Unless we're giving like somebody directions on how to get somewhere, we usually don't say north, south, east, west, or right, left, up, down. Usually, you know, if we're saying like how fast we were going on the freeway, we might say we were going 72 miles per hour. Well, if I was on 71 north and I was heading north, which hopefully I would be if I'm on 71 north, then I could say my velocity was 72 miles per hour north. If I include the north, then that's a velocity. If I just say 72 miles per hour, that's a speed because I didn't include direction. So it's kind of science being a little specific, and you just have to be accurate in terms of science. And the one video we watched said that. It was like, hey, sometimes like our science meaning is a little bit different than our everyday meaning of something. And so speed and velocity are that way, right? We say speed incorrectly a lot when we really mean velocity and vice versa. But in science, make sure you're being very specific between the two. And we'll get to those details in a minute. So here's some examples of some scalar things. A distance of 2 meters. I don't know which direction. It's just a scalar quantity. It's giving me distance. I don't care about the direction. Speed of 40 kilometers per hour. Again, direction is not needed because it is speed, not velocity. It doesn't make sense to give a direction with time, ever. Like 3.4 hours. Like, I can't think of a single situation where you would need to say direction with that, right? Making time always scalar. Now, if you have like a kilometer per hour, you have the hour included, but you're going for how many hours, that set amount of kilometers. So that goes together, but just hours or time alone, we don't need to worry about it. So this is just kind of like a little flow chart. We have different types of physical quantities or amounts. Scalar ones are magnitude in units. Vector ones have magnitude, direction, and units. Right. And again, it's just easy to forget the direction. You guys are pretty good realizing, okay, we need to include a unit. Problem is when it is something that is vector, you have to use that direction. Okay, so let's just do a quick little check. On your paper, I think you have like a little blank. Take a second and put an S if you think it's scalar. Put a V if you think that it is vector. So on your notes, you're just going to be writing S or V by those different quantities. We're going to decide if they're scalar or vector. sleepy faces this morning. Dark, it's dreary. Coming off a 4-day weekend. Okay, looks like everybody's got it. So, 16 years. I'm just gonna kind of randomly call on people. What do you think, Cheyenne? S for scalar. Oh, geesh. All right, 50 kilometers per hour. What do you think, Rory?
Vector.
Okay, do you see a direction?
Okay, no.
So which, we like the scalar, good. What's our next one? Cade, 6
Okay.
kilometers north,
Vector.
good. So again, that capital N in the brackets means north, and so that makes it vector. 2,000 kilograms per meter cubed, so this is a volume, if you recognize those. What do you think, Abigail? It's gonna be scalar or vector? Good, there is no direction included. 800 kilograms, what do you think, Anthony?
Scalar.
1.0 kilograms per week. What do you think, Austin?
Scalar.
Scalar. 20 meters per second south. Dylan, what do you think?
So it has a direction.
It does.
So it'd be vector.
Absolutely. Good way to reason that out. 400 newtons, we haven't talked about the newton yet. 400 newtons down.
Newtons of force?
Yes.
Oh.
400 newtons pulling down.
Who'd be pulling something down?
Hmm?
Down is a direction, vector.
Okay, very nice. So it doesn't always have to be like a cardinal direction, like north, south, east, west. Sometimes it can be up, down, left, right. 6 centuries.
That's time.
What? Hold on. Let's let somebody else. Even though yeah, it is a time. So Michaela, what do you think? Good. All right. I think is that the last one? Yes. Okay. So now that you know, if you see a direction, it's vector. If you don't see a direction, it's scalar. There's going to be 2 ways to show length. There's 2 quantities, a distance and a displacement. This is another way that we almost always incorrectly use these. We don't normally say displacement, right? When we're talking length of something or how far something is traveled, usually we just stick with distance in our everyday language. In science, distance and displacement have more specific definitions, okay? We talked about water displacement, right, with finding the volume of an irregularly shaped object. And so that was how much the water changed when you put in that unknown object. So we've kind of talked about displacement a little bit, but now we're gonna kind of like officially do it. So distance is a scalar quantity, which no direction, is identified. So we don't have to include the up, down, left, right, north, south, east, or west. We don't need any of that. Distance is basically like the pathway, all right? So the ant started here at position A, it wandered around like ants will do, and then ended up at position B, okay? So it doesn't matter, like the direction, we don't need to include that. Basically, it's just following the path, right? In another way, it's almost like the perimeter or like the whole outside pathway. So when it's more of like a square or a rectangular path, the perimeter is kind of an easy way to look at it. So distance includes the total length of the path. It is the entire trip. Okay, so when we went to Fort Worth, it was 1,100 miles one way. And so it was 1,100 miles there, and it was 1,100 miles back, so it was 2,200 miles total that we traveled, okay? That was the total distance that we went. We started at home, and we ended at home, though, so keep that in mind. So that was our total trip of 2,200 miles. All right, now there's this other thing called displacement. So displacement is another way to talk about, like length or a trip or like the space traveled. All right, so this is going to be something that is vector. So vector will have a direction, okay? Vector will have a direction. So if you look at this picture, the distance is shown here at the top, kind of in blue. This is the whole pathway. This is the entire trip. Displacement only cares about your change of position. So if you started here and ended here, my displacement is this line right here. All right, so the distance is the whole trip. My displacement, though, is just where I started compared to where I finished. So if we're talking about our trip to Fort Worth, we started at home and we ended at home. So our displacement was actually 0 miles. Didn't feel like 0 miles, I will tell you that. Okay, the distance was 2,200 miles. Displacement was 0. So sometimes the distance and displacement are the same. Sometimes they are going to be different. And in this example, they're different, right? You can see this pathway is much longer. That distance is longer than my displacement. So it only measures the start to finish, and how we got there does not matter. Okay. And so to find displacement, we're going to look at our change in position, which is our final position, subtracted from our initial position. Remember our little triangle for delta? That means change in. So you see this little change in x, okay? X is just a generic kind of variable that we give for position, right? So if you're talking, and I think the reason that they use the x is because a lot of times we're talking like horizontal. If I go from here to there, that's a horizontal change, right? When we talk about a vertical change, like this water displacement idea, we could use y, because that's like our y-axis on a graph. So sometimes you might see change of y for displacement. Typically it's going to be change of x, but if you would happen to see the change in y, I don't want you to panic and freak out thinking you don't know what that is. It's just looking at a graph is your vertical for y-axis. Horizontal is usually x on our graph. And so they kind of, use those same variables, the x and y axes, even though we're not really talking about a graph here. So that's kind of why, if you're wondering. So usually, though, you're going to see our change in position as the x. So what do you think this F and this I stand for? What do you think those mean?
Final position and initial position.
Very good, yeah. So it's our final and our initial. What does initial mean? What's another word for initial?
Starting.
Starting, beginning, okay? So we're taking our ending position and our beginning position and we subtract them, right? Also, sometimes that displacement can be shown vertically, so we'll use the change in y, and then it would be our vertical change final position minus our vertical change initial position. And we did that already, right? We looked at our volumes and took the final volume minus our initial volume to get the change in volume, which would be attributed to, the irregularly shaped object that we put in that cylinder. Is that all sounding okay? Like you guys are like giving me blank looks, so I just want to make sure. Okay, so here is a practice problem. An ant walks to the left on a ruler and begins at the 10 centimeter mark and stops walking at the 50 centimeter mark. What is the ant's displacement? Okay, so I think I have it on here. Yeah, so we're going to circle just like we always do. We're going to circle what we're solving for. This is what we did with the density problems. We underlined the volume and the mass, circled the volume if that's what we were solving for in that case. So we're solving for displacement, right? And so now we're gonna underline some of the information that's given. All right, so what do you see as the final position, that XF? Where does that ant end? Where does it end? Dylan, what do you see?
At the 50-centimeter mark.
Okay, so let's underline that. And I'm not sure if you guys need to underline that or if it's already underlined for you. Okay, so 50 centimeters is underlined. And so now I'm gonna fill that in here. Now I need to underline another piece of information. And what we're looking for is the beginning or the initial. So what do you see there, Stewie? Where did that ant start? Good. So let's underline that and then fill it in. So now we just use our equation, right? The equation for displacement is our final position minus our initial. Well, we have that, 50 minus 10. Okay, so the ant moved 50 centimeters. Now, here is how you can determine the direction, all right? So if the ant is here on the ruler and he walks to the left, the ant started here, right? I'm gonna see that. Okay, so the ant started here, and let's do this. Started here for go, went this direction. To figure out the direction that the ant went, what I always tell people, if you put your pencil at the point that it started and lay it and point it towards the direction that it ended, so put it at the XI, point it to the XF, whatever direction that pencil is pointing, that's the direction, like the overall direction that the ant went. And it's pretty easy on a problem like this, but like on some that you'll see when we make multiple turns, trying to figure out what direction, that's the easiest way, right? Or you can put your finger, right? So if you put your finger on the initial and you point to the final, you just ask yourself, which way am I pointing? Left, okay? So that's kind of where that comes from. And so that is a displacement. Now, here's another one. Displacement is not always equal to the distance. In that case it was, right? Because the pathway was 40 centimeters and the displacement was also 40 centimeters. Here is another example. A dog stands up from his bed, he walks 5 meters, stops, walks back, and goes to sleep. Okay, so he gets up, walks 5 meters, turns around, and walks back 5 meters. His displacement is actually going to be 0. And the reason that it's 0 is because his final position and his initial position were both the same spot. Right, so just like my trip to Fort Worth, started in my driveway, went 1,100 miles, went 1,100 miles back, and ended in my driveway. Right, so that was 2,200 mile trip, but my displacement was 0 because I started and stopped in the same spot. Same thing with this dog. Okay, now, what would his distance be? What was the total path or trip that he took? What do you think? Okay, yeah, because he went 5 and then 5 back. Okay. So again, when the displacement's 0, it doesn't really make sense to use a direction. You can just tell me 0 steps or 0 kilometers or 0 whatever. Include the unit still, but I don't need a direction at that point. All right, so something that might kind of help tie a little of this together is these values can be considered positive and negative. All right, so movement to the right or east is considered positive. So here's east, which is also like turning to the right. Movement to the left or west is going to be considered negative. Think of like a number line. All right, so sorry, a little bit of math today. Think of a number line. And you know that pretty easily, right? Anything, if this is 0, anything to the right is gonna be positive, anything to the left is going to be negative. And so when using displacement vertically, the same kind of holds true. Anything that is north is gonna, or up or positive, and down and south are negative. So really we have 4 positive displacements and we have 4 negative displacements. North, east, up, and to the right are all positive. Down, south, left, and west are all always gonna be considered negative. And so as you get into math, if you assign a negative value to something, you know, you're not gonna combine them, you're gonna actually end up subtracting them. And so that's why these directions are kind of, they can be important. Okay, so hopefully this reminds you like of a coordinate plane system that you have in math, where you have all 4 quadrants. So if you have, I think I have, yeah. So, you know, if you're looking at coordinate pairs, and this is your x-axis, and this is your y, you have quadrant 1, 2, 3, and 4, right? So anything over here, right, this is, you know, always gonna be positive, because it's up and to the right. If we're just looking this way, it's to the right, so this is all positive. So keep in mind that some of those things that you already know. All right, let's go ahead and we're gonna stop on that one. And we need to go back to some videos.